Hello, everybody. My name is Jake Cochran, and I chose to look into how math is used in architecture. So I mainly focused on the calculus aspect, but still like to look into some of the other branches used. So, for example, ratios are used in the planning stage, normally in the blueprints, quite a bit to scale down what our structure is going to look like. Um, so, for example, we take into consideration every little detail, wall thickness. We have templates for everything. You can see in this bathroom here, template for a toilet, template for a shower. We even have how much space a door is going to take up when it's opened. Um, all this stuff is considered before we even build. You can also use ratios to make a model of the building before construction starts. That way we can have a physical representation of it, and we can see it and have a better idea of what it's going to look like once it is built. Uh, Looking at geometry, geometry is applied fairly obviously, I think. I mean, every single building is just made up of, an arrangement of shapes, but I'd mainly like to mention triangles. Triangles are really useful in architecture for support. You can really see this in bridges. Bridges are just an arrangement of triangles to, provide it the most possible support while using the least amount of material. Um, this keeps our weight at a minimum and our strength at a maximum. And that's really important in the sense for bridges, but also um, when looking at a structure for a building, a roof is normally a triangle. Gives it pitch, and so weather can run off of it as well as providing it uh, a strong top to protect the rest of the house. So looking more into that, we can see in construction, we use a good bit of trigonometry to help with roofs. For example, we're going to have this here, and normally the slope of our roof is predetermined, and by using that, we can find our height. And like I was saying, how triangles are used for support, you can kind of see that here in a roof. But we can also use trigonometry in construction to kind of find a how much material we'll need to fill an area or something like that. So for example, we needed to fill this area here. Say we want to build a house on top of this, but we need to fill all this. Well, we can measure this hill. That's going to be our hypotenuse. Then we can measure this here. Say this is going to be a retaining wall or something we're going to build. So we know how high that's going to be. And then by using those two, we can find this angle here. Now we have all we need to find our opposite side here. Our length is measurable, and then using those four, we can find the approximate area in here, so we can know how much material to buy to fill. So yeah, in trigonometry or in construction, trigonometry is used good bit to save time and money. Now for calculus, we get right in here. Let's see. There's a lot of different ways calculus can be applied, but I looked at it more of a sense of more simpler sense than just the acting force wind has on a building. So you're looking for the force here being applied on this side of this building, of this 10 by 7 foot building. So force can be found with this equation here. Pressure is equal to our force over our projected area. We can turn this equation into force is equal to pressure times area. We can find our area, just 10 times 7. And now we can find our pressure. Pressure is found with this equation here. Pressure is equal to CE, our gust factor. So it's kind of based on the environment of where we're building. times CD, our drag factor. So that's going to vary depending on the shapes, the aerodynamics of our affected side. QS, our wind stagnation pressure. This is the amount of force the wind has. And then IW, which is our importance factor. Importance factor, really, it just varies based on kind of what your building is going to be used for. So say it's housing a hazardous waste, this is going to go up. Or if it's has a lot of really, really expensive equipment, it's going to go up. But for our example, we're pretending this is a residential building. So it's just a 1 for importance factor. And all of these three here are going to be predetermined. It will be found before we get to this stage here. So for this example, I'm going to be using these numbers. Now, to find our wind stagnation pressure, these are the equations we can use. You use each one depending on what you're looking for. So this is for pounds and this is for newtons. So since we are working with miles per hour and pounds, we are going to be using this one here and substituting V for our wind speed, which is 70 miles an hour. So I'm going to go ahead and plug that into this equation here, which gives 12.544 pounds per square foot. So that is how strong our wind is. Now we can plug that into our P here. Now that we have each one of these three are right here, and then we have found our QS here. Plug all of those in here. That gives us approximately 11 pounds per square foot. Now that is how much force the wind is acting on this surface here. So now we have both our P and our A. We can go ahead and plug them in to give us about 75 pounds per square foot. And that is our total acting force on this side of this building from the wind. So whenever the structural engineers go into to look at how this building needs to be supported, that's something they'll consider. And this is just one example on how wind affects it, but we can also use this to determine like fluctuations in weight, say if it's a skyscraper or something, or the accumulation of moisture, say in rain, whatever, is all determined using calculus and accounted for in the construction. Anyways, I hope you guys learned something, and I hope you enjoyed. Thanks.